Hey guys, Jesse here from Elevate with another chemistry video. Now again, we're going to be tackling some enthalpy questions here. Hopefully you can see that this is from the 2012 chemistry exam, the second one, and it's from the VCE course. And we're looking at question 6. And as always, the first thing I want you to do is to have a crack at this question. Now I will note that the only question that I actually want you to fully go up to is only go up to question B, so just 6A. So have a crack now. Fantastic. Now I hope this all went well. The questions have gotten a little bit more challenging, but hopefully keeping up with it. Now we're going to be focusing on two things right now, both the calibration constant calculations and also finding enthalpy change given various values. So let's start off with that calibration constant. Now hopefully this bit should be pretty straightforward. We're looking for the calibration constant, and that's energy per degree centigrade for the calorimeter and its contents overall. So we're going to need both energy and we're going to need also a change in temperature. Hopefully that's pretty straightforward. Now energy is equal to, well, what? Unfortunately I'm not actually given energy anywhere in here, so I'm going to have to be a bit creative and find it somewhere. Now thankfully I've got volts, I've got time, and I've got a current. And in your data booklet is the equation energy equals VIT. So we're just going to simply use that by multiplying the volts, the current, and also the time. And of course, the time needs to be in seconds, guys. And the reason for that is because of the current actually deals with seconds as a unit. And if we plug all those numbers in, we get 1.42 by 10 to the 3 joules. Now first things first, I noticed that this calibration constant is in kilojoules, so let's actually convert that into 1.42 kilojoules. And hopefully you know that this 10 to the 3 allows that conversion to kilojoules nice and easily. So now I've got an energy. How do I get the calibration constant? Well, if you're a little bit stuck, you've gone blank, how can you work out how to do it? Now thankfully it's actually telling us the calibration factor or calibration constant is equal to, and I'm going to write this potentially a little bit weirdly, kilojoules per degree Celsius. And notice that I've literally got an energy and a temperature on the bottom. So that's exactly what I'm going to do here, guys. And this principle is called dimensional analysis. It means that whatever sort of units that I've got as a final answer, my units on the other side of the equation have to be the same thing. So all I'm going to do is grab that energy that I just found, 1.42, and remember, kilojoules, and I'm going to divide that by the temperature change. And I've got right here, the temperature change was 0.593. Plug that in, calculate that, and you get 2.39 kilojoules per degree Celsius to the -1. So what I really want you to understand here, guys, is this bit right here. It's so useful. And I'm going to use a simple example just to show you what I mean. Now let's take, for example, molar mass, which of course is equal to grams per mole. And we also know that molar mass is equal to mass divided by moles. These two things are related, guys. If somehow I forgot this one, I could get it from the fact that it is grams per mole. Whenever you're given units, you can use that to your advantage by working out how you convert it into some numbers or some equations that you're actually pretty familiar with. And this thing's called dimensional analysis. I guarantee if you continue with science or end up doing engineering or something like that at uni, you will encounter this stuff and you will love me for the fact that you're dealing with it now. Alright, so let's move on to the second part of the question here. So student then used this calorimeter to determine the molar heat of combustion methanol. Let's deal with the numbers. I don't really need to read the rest of that. 0.934 grams of methanol, increase of 8.63 degrees Celsius, and of course, I've got this equation. Now I need to use this experimental data to determine the value of H. So I'm not actually given the heat of combustion for this reaction. Instead, I'm going to have to work it out myself. Now, as always with chemistry, I've got something as mass. Let's actually convert it into moles first. That's nearly always the case. So I'm going to go moles of CH3OH, methanol. Of course, that's reacting. And that is equal to our mass divided by our molar mass of ethanol, which you can either work out or memorize as 32. And that gives us 0.0292 moles. Now, how are we going to use that? Okay, well, the energy that's actually released is going to be equal to our calibration factor times by the delta T. And well, how do I know that? How am I going to remember that? Well, let's go back to this dimensional analysis concept. So calibration factor was equal to kilojoules per degree Celsius. And temperature, of course, is degrees Celsius. So notice that if I actually multiply these things together, though these cancel out, and I'm actually left with kilojoules. So again, if you're ever stuck trying to remember some sort of equation, use this dimensional analysis trick, cancel out the units, multiply the units, whatever you have to do, and work out what your answer is. So my energy released, I just worked it out then, is my calibration factor. So 2.39 times my delta T. In this case, it's 8.63. Don't use the one from the previous question. And that is going to get us a total energy release of 20.6 kilojoules. Fantastic. Now, what do we need to do from here? Well, this is my total energy released. And what we're asking for is delta H for the combustion of methanol. And what that means is per one of these equations. And the easiest way to do it is to work out per mole and then go to per equation. So let's start out by working it out per mole. So the total energy released was 20.6. And to get it on a per mole basis, well, we simply divide by the number of moles. So we're just going to take out 0.0292 divide by apologies there, guys. We're going to simply take our 20.6 divide by 0.0292, and that will give us an energy per mole of 706 kilojoules per mole. Now again, this is dimensional analysis over here. It's my friend, it's your friend, you should use it. Now delta H. Well, delta H actually has 2 moles of methanol. But notice that they're on the left-hand side of the equation, and that means whatever this delta H business is, we're actually going to be grabbing the negative of it because it's on the left-hand side. So delta H is equal to simply -2 times the value we just got of -706 kilojoules per mole. And that's going to get us -1.41 by 10 to the 3 kilojoules per mole to the -1. And of course, you could have this as joules, you could have this as whatever, but as long as you remember that you have this negative value here because it's on the left-hand side, and of course, you end up releasing energy. And hopefully that's pretty obvious because we've got this combustion reaction going on there. Fantastic. Alright guys, so that's it from this video, and I look forward to seeing you for the next question.